Good afternoon and welcome to all of you. My name is Marica Manisera and from University of Brescia in Italy, and I am the chair of this invited paper session entitled Advances in Sports Statistics, one of two. We will have three speakers and a discussant I'd like to thank warmly. We'll also talk about football today. In the aftermath of Euro 2020 final, the victory of Italy has shown that the statistical models can be very useful to predict the winner, but there is always the epsilon in the model that makes the game always beautiful to see until the end. So I now give you just a couple of communications. First of all, it's a pleasure to announce you that tomorrow another session of Advances in Sports Statistics is scheduled among the non-live invited paper sessions. And the organization of this session, is one of the activity of three interconnected research networks that are the ISI Special Interest Group on Sports Statistics, the Big Data Analytics in Sports, and the S-Training Group. And here you can see the websites where you can find more detailed information about them. So now our three speakers are ready. So let's start with Professor Christophe May. I can stop my sharing. Okay, so Christophe, you can start your sharing of your screen. It's a great pleasure for me to introduce Professor Christophe May, who will give us a talk entitled Statistics Meet Sports When Figures Are More Than Numbers. So Christophe, the floor is yours. Thank you.
So thank you very much, Marica, for the kind invitation, and welcome everybody to our session. So after this indeed great victory of Italy yesterday, I will talk today about where we can find statistics in sports in general. And to this end, I'm going to start. Can you see my slides advancing?
Yes.
Nobody complains, great. So to this end, I will first start with some motivation and show where sport analytics, that's the terminology that we use for statistics and machine learning in sports, how it has come to fame, and I will give just a few striking examples to show you indeed that this has a deep impact on sport. And then second part will be about current research and open questions, because there are some really interesting, challenging statistical questions that are out there for everybody to address. So let's get started with the genesis. The father of sports analytics by most people actually is considered to be Billy Beane. And he was into baseball. So after the 2001 season, Billy Beane, the manager, was shocked by the bad performance of his Oakland Athletics baseball team. He wanted to make a change. He wanted to improve this. So in order to do this, what he did is he hires an economics graduate from Yale in the person of Peter Brandt. And this guy, he's an econometrist. So he knows about statistics. And what he does is he takes a completely new take on setting up a team. Namely, he's using sabermetrics to hire players. So not the typical idea, okay, this player might be good, so I take him. No, this time he builds himself on sabermetrics. And what is sabermetrics? It is the statistics of baseball. That's the official terminology for it.
Christophe, sorry, can you put the slides on full screen mode?
Sure, can I do that?
Sorry.
Let me see. Can you see it under this form? Or is it black?
Not yet.
No, it just didn't change.
Okay. Yeah, I don't know why. I have a problem. Actually, I cannot do this because when I try to do this, he tells me that screen sharing is stopped.
Okay, it's fine. We can see everything this way.
So. Okay, yeah, sorry. It's a bug. No problem. So he used statistics in order to see, okay, which player could bring us the most in terms of numbers. And that was something completely new, but it led to a big success. they didn't have to spend a whole lot of money. They could deal with small amounts of money, but they found the right players, which others would never have taken and also did not take. And so this big success has really revolutionized professional sport because it showed everybody that with a clever strategy based on data, you can actually have a big success. And this big success has been, there has been written a book about it, Moneyball, and it has been made into a film. And here you see Brad Pitt, who was starring in this movie, which I can recommend if you want to have a look at how this all started. Another striking example is basketball. So for those of you who are basketball fans, you will have noticed that there has been a change in the playing style, especially in the NBA. For those who don't, typically until 10 years ago, three-pointers were not the most common shot because they had a higher risk of not going into the basket. But in the recent years, more and more players, the tactics of the teams are based around three-pointers. So this has really completely changed the entire playing style in basketball. And this all began when Greg Popovich, the head coach of the San Antonio Spurs, noticed that, so here you see the three-point line, that actually the three-point line is closer in the corner than on the rest. And so he asked his players to take more three-pointers from the two corners. This has led to a new idea about how you could view three-pointers. And from that moment on, there has been a three-point revolution because they have seen, okay, if we change our playing style in such and such a way, we can shoot more threes, we can train more threes, and we will get more points. And so here you see NBA team points from 3 points per game. You can see how this has increased. This is the lowest per team, this is the highest per team, the league average, but you can clearly see an increasing trend between 2003 and 2017. And this trend is still continuing. They remain at this very, very high level. And really, I invite all of you, take a look at some 90s YouTube videos. Michael Jordan hardly ever took a three-point shot. And then take a look at what is happening nowadays. You have the feeling it's a completely new game. And this is all due to the three-point revolution. So there are several more examples, but since we are short on time, I just stick to these two and now go on to some current research. But for this as well, I'm starting with basketball because nowadays more and more data per match are recorded. The scores, of course, the rebounds, assists, steals, turnovers, all this is classical, but also more and more possession gets recorded, where the shots have been taken, more and more data are being done. And so this also begs for good analysis. And here I have to make a little bit publicity for our chair, for Marika and Paula. They have written a great book, Basketball Data Science with Applications in R, that you can see here, which has really meant a big step forward in basketball analytics. And what they also did, accompanied with this, goes an R package called Basketball Analyzer, with, of course, the typical R in capital letters. So what can you do? Here are some examples of advanced statistical analysis that are possible with this package and that you can do now. You can check the association between some of the variables like possession, scores, rebounds by means of pairwise linear correlation. If you want to see how similar teams are or players are, well, you can use multidimensional scaling. To get relationships among players and the impact of the interaction on the team's the final success, so how good are players interacting and what does this imply for the success of the team, this can be done by means of network analysis. So already now you see that the classical statistical ingredients all have their place and they lead to very new discoveries within basketball, new insights that the clubs are eager to get. The frequency of shots in time or space can be done by means of classical non-parametric density estimation methods. Or this is something that Marika and Paula have also worked on. Before, in the 90s, there was a clear subdivision of the roles. You had the center that was there to score close to the basket. You had the point guards, the shooting guards, power forward, small forward. The positions were clearly defined. This has changed. So you can try to redefine roles and see which players fit better into this type of mode. How can this be done? It's hard to do it just like that, but cluster analysis is there in order to help to redefine these roles. And much more is possible. An interesting question in basketball is, for instance, to build probabilistic models for the final scores of basketball games. That does not exist much so far in order to predict the outcome of a basketball game. So I think that's something where statisticians definitely have a word to say among many other things, but that's one that I deem particularly interesting. Second example I want to mention is positional data. So here I'm taking this from the book chapter Analyzing Positional Data by Brevard, Lazar, and Meyer. And this is in a book that I have edited together with Yves Dominici. We call it Science Meets Sports, when statistics are more than numbers. So in many sports, you have these positional data. What does that mean? There are cameras everywhere. And so at every moment, the position of a player is being recorded in on the basis of 20 images per second. So you know a lot of where every player is. And with this, what you can do is, well, you have his position can be two-dimensional in an XY axis or three-dimensional. Then you also have a Z component. And with these positions PT in two or three-dimensional space, you can also then, for instance, measure their the speed at which they go by just looking at the difference of what they are running divided by the time. And with this, you can deduce a lot of things. For instance, as I said, speed or velocity, and also the running direction. And then you can make statistics like these here. You can, for instance, see for how often in a match is a player doing a sprint or a run, a jog, walk, stand. And then you can compare with respect to the position. Of course, you see that stand and walk is mostly done by goalkeepers, whereas goalkeepers hardly ever make a sprint. And then you can see, oh, what's the difference between defenders and midfielders? It's quite interesting that the defenders are doing nearly as many sprints as the more offensive players. But what is even more interesting for coaches is this here, the zones of control. What is a zone of control? Well, you can see it here on this image. Take, for instance, this is the keeper here. This zone here shows all the places on the field where the goalkeeper here would be the first to be there. He will be the fastest to be in every of these areas. And so for instance, for this player here in blue, the defender of the blue team, this is his area, his zone of control, where he's the first. If the ball lands there, he will be the first on the ball. And you can do this at many different moments. So from this analysis, the coaches can see, okay, wait, if I would tell my wing player to more go into this type of rooms, if the players are like that, well then, okay, then he would have better chances. And I could change my tactics like this. So this is really a very, very strong new tool that coaches can use in order to improve on their tactics. And then you can, of course, also see here, you can also measure where is the offside line. There is really a lot that you can do with this. And the third and last point I want to mention is the modeling of football matches. So with this, you can, for instance, try to predict outcome of a tournament, as like the tournament of that just finished yesterday. And so I'm going to show you how you can model the outcome of a single football match. The idea here is inspired from a 1982 paper by Maher, but mainly nowadays gets referred to by the paper Kalis and Soufras in 2003, a very nice paper. The idea here is to assign to every team a playing strength by means of a model, and this is the bivariate-Poisson model. Why bivariate-Poisson? Well, you try to model the number of goals that every team scores, and this is a count variable. So you have to count, and that's where you need the bivariate-Poisson model. So if you write YIJM, the number of goals scored by team I versus team J during match M, then the joint distribution of the final score of both teams, so the probability that the first team scores X goals, the second team Y goals, is given by this expression here, where you see lambda IJM is the expected number of goals by team I, and lambda JIM is the same for team J. These are the typical Poisson parameters. And since it's a bivariate Poisson model, there is one more parameter, lambda C here, which is a covariance parameter to measure the interaction between the two teams. So with this, you can actually model the outcome of a single football game. And then what are you doing with this? Well, what I haven't said yet is how the strength of the teams enter this modeling, because now, yeah, how can we define these parameters, lambda IJM, lambda GIM? It is done by, under this form here. Ri and Rj are the respective playing strengths of team I and team J. So if team I is stronger than team J, then clearly this is positive, and it will increase the number of goals that team I will score against team J. Beta 0 is just some intercept. If both teams are equally strong and there's no home effect, then that would be the average number of goals scored. And here H is a home advantage parameter. It could be negative. You don't know. Typically it's positive, but could be. So this is to take into account if a team plays at home. And then what you do is, well, you have to estimate these parameters. So if M matches are played, then you can actually estimate all these parameters and hence also the playing strength of the teams by means of simply the maximum likelihood procedure. So here you take the product of all the different matches where little YIJM is the actual score of each match. And so by maximizing this likelihood, you get these parameters. Now, what can you do with this? Many things. You can, of course, make predictions of games. But what you also can do, and that's an example of use that I'm finishing with that. Suppose that we are in a situation that a season has to be stopped prematurely after X matches played. This reminds, of course, of what has happened last year with Corona, when it was unclear a season is stopped. How should we evaluate it? Well, here is one fair way that we suggest to evaluate a season. Suppose that after these X matches, we have estimated all these parameters. And what we can do is, we can actually simulate the remaining games 100,000 times by this model. You take the average over the 100,000 simulations, and so for every team, what we get is the probability to reach every possible position. We have named this, together with my PhD student Hans van Eetvelde and Lars Magnus Wattum, we have called this the probabilistic final standing calculator, because it gives you for every team the probability to reach each possible final rank. And so what is good is that this model takes into account matches that are still to come, instead of simply saying, okay, we stop here and that's the final standing. No, we take into account what is still to come, and because if a team has to play against stronger opponents, well, this team will score less than if it were against weaker opponents. And so I'm giving you here an example. This was from the League One from last season, from the season 1920 that was stopped prematurely. You can see that PSG had 100% chance of being first. Marseille, very strong chance of being second. But that's what it looks like. Toulouse was clearly among the last two. We can compare this to the actual evaluation of the League One. So this is a kind of ranking based on expected ranks, where you see, okay, PSG, Marseille, Rennes, Lille, Lyon. That's what our model would say. What was in reality? Well, in reality, they stopped the season. And then what happened is that Lyon only was 7th. They still had to play against weaker teams. So in our model, Lyon actually is seen as being 5th. And so rather being, it should be admitted to the European Cup, but it wasn't. So this is one way how you can get a fairer ranking by means of this modeling of the games. And now, of course, this is one way, the bivariate Poisson. There are many more ways of doing this. For instance, you could add, instead of one strength parameter per team, you could give two, an attack and defensive strength. You could, instead of just taking the maximum likelihood, you could take a time series approach. You could take a Bayesian approach. There, our discussant is an expert for that. You can also, instead of the bivariate Poisson, use copulas for the dependence between scores. Ask the next speaker about this. Then, instead of the Poisson, you could also use other count distributions, such as the negative binomial or the viable counting model. I refer here to a very nice paper by Boschnakov et al. And of course, instead of modeling the score, you could also simply model the three-way outcome by means of the so-called Thurston-Mosteller model or Bradley-Terry models. what we have done is, with my PhD student Hans, we have done a partial comparison in which we showed that modeling only the score is less good. Than modeling where we showed that modeling only the outcome is less good than modeling the score, because you're throwing out information. But what is truly the best model among all of this? This is still an open question that I believe would be really interesting if an answer could be found. And that's it. I thank you very much for your attention.
Thank you, Christoph, also for respecting your time. Are there any questions from the audience? If not, I will go on with the second speaker, and then we will have maybe some minutes in the end of the session after the discussion we have by Leonardo Gidi. So please, Andreas. Okay, thank you. So I'm giving now the floor to Andreas Moll with a talk entitled "A Machine Hybrid Machine Learning Approach for the Prediction of International Football Matches."
Yeah, Marika, thank you very much for inviting me. I am trying to make the full screen mode, and I hope that you can now see it in the full screen mode.
Yes, it's okay.
Perfect. Yeah, so I'm talking today about a hybrid machine learning approach for the prediction of international football matches with an application of the Euro that has just finished yesterday. And actually, I started this kind of research in 2012 when I was first trying to model and predict the European Championship 2012. And since then, there was a long list of collaborators that were joining me over the years. And we joined our forces and tried to improve these models over the years. And I will show you today kind of the latest result of this research. And that is why you see here so many names on that list. So first of all, it's of course time to congratulate the Italian team. So we already discussed about this at the beginning of the session before the audience joined. So it was very well deserved, definitely from the way Italian was playing. I think they were really like a team of 26 friends, which is very important in football, that the team goes along very well with each other. And I had the very lucky coincidence that I could watch the game yesterday at Lake Como here in Italy. And I can also say it was deserved for the people, because I was in a small bar with 200 young people and they were just crazy. They were singing like 120 minutes in a row without stopping. And it was just amazing. So it's definitely in some sense well deserved. So, but now let's switch back a couple of weeks before the tournament starts. And when such a big football tournament is upcoming, of course, all the fans are excited about which team has the highest chances to win the tournament. But not only who will win, but also maybe which teams will surprisingly drop out at an earlier stage of the tournament. I could, of course, also put a picture of Germany here, because, again, they did a quite horrible job in this tournament. So, and also before the tournament starts, there's many things going on. So, for example, there is the bookmakers, where you can find odds on all the teams, telling you chances, how they suggest that the teams will win the tournament. In Germany, we have also something that is called Kicktip. It's a game where you can you can invite your friends, and then you can all put numbers, like you can put the results, the predictive results for each game, and then you get points the closer you are to the real result. And that's what typically many people in Germany do when such a tournament starts. And then there is, maybe you heard about them, these animal oracles. So for example, in 2006, we had the famous octopus Paul, who was always trying to pick one team before a game in an aquarium. And also in 2018 at the World Cup, there is this hungry cat that had to choose between the two pots. And you can see maybe there was already some bias, because the lady, it seems that she puts the cat quite close to the Russian flag. So maybe there is some bias. And so in general, of course, as a statistician, the question is, how can the prediction of such a tournament or of single games can be done a bit more sophisticated maybe than with these animals. And so we will start with the data situation right before the start of the tournament. And of course, I want to use the current or the Euro that just finished yesterday as an example. So actually what we did is we collected covariates together with the game information of the 4 preceding Euro tournaments. And for all these tournaments, we took the covariates of the specific teams at that time. So we included, for example, economic factors. So like for each nation, we collected the GDP and the population size at the time of the respective tournament. We included some variables to check for the home advantage. We had a dummy, which team is the hosting team, and which teams are neighbors to that hosting team, because maybe there's a less a traveling distance for the fans. We also included sportive factors like the market value, the FIFA ranking, and so on. Factors describing the team structure. So we collected the first and second largest number of teammates that played together in their national club, the average age, and we collected how many players are within the national team squad that reached at least the preceding half final of the Champions League or of the Europe League, which both take place just a couple of weeks before the Euro. And also we counted the number of players abroad. We also had a few factors describing the team's coach, like the age of the coach, and a dummy, whether the coach has the same nationality than his team. And finally, and this is maybe the big progress that we made in the last years, we collect additional ranking type variables from other statisticians. So for example, Christoph Ley, who was just the preceding speaker, he and his team, they calculated with kind of a Poisson ranking model, which we have just seen on the last slides of Christoph's talk. They calculate a current ability ranking based on all the historic games of all the national teams of the last 8 years. We also received from Achim Zeilers and colleagues from Innsbruck, we received additional ability variables that are based on the bookmakers' odds. So actually they averaged about 20 bookmakers and got some abilities out of that. And finally, Lars Vatum from Molde also provided us plus-minus player ratings. So we actually include 3 additional variables that come themselves from statistical models. And hopefully we can improve our predictive performance by this. And in the end, we incorporate all these variables as differences between the team whose goals are considered and the respective opponent. But you will see this in a second when I show you a bit more detailed how the data look like. So here you see actually how we come up with a final data set on which we can train our models. So first of all, we have the pure game results. So here you see a bunch of games from the 2004 European Championship. So you maybe remember that Portugal was losing the opening game against Greece, who later became the European champion. And at that time, the Portuguese team was quite well with these historic abilities, also with the bookmakers' abilities, the average player, plus-minus ranking. And for example, Portugal was placed 20 in the FIFA rank at that time. Spain, for example, was placed 3 at that time. And the Greece team was only on place 34. And now we merge these data in the way that we get 1 observation per team per goal. So here you see the opening game between Portugal and Greece leads to 2 observations, the Portuguese goals and the Greece goals. And then we incorporate all the additional covariates in the form of differences. So for example, here you see from the perspective of Portugal, we had a difference in the FIFA ranking of -14. But when we now take the perspective of the Greece team, then we had a difference of +14, which actually tells us that from the perspective of the FIFA ranking, the Portuguese team was the favorite team here. And this we did for all the historic matches of the previous 4 European Cups and with all the covariates that you have seen on this slide. And so we get a quite enormous data set on which we can now train our models. And as Christoph already said, a very important role in the past years have played these Poisson-based models. And we actually also started our research using these Poisson-type models. And if you are more interested into them, together with Gunther Schauberger, we have published a small summary where we summarize all these type of regularized Poisson models. But in the later years, since the World Cup 2018, we actually changed from those Poisson regression models to random forests, which actually turned out to be even more powerful, even though, of course, we lose a bit of interpretability. And let me quickly recap the idea of the random forest. So it was originally introduced by Breimann in 2001. And the basic idea is that we aggregate a large number of either classification or regression trees, depending on the task that we have at hand. In our case, we model the goals, and that is why we have actually a regression task. And the idea is then that in order to get final predictions, we aggregate the single trees. We would either use majority vote in classification, or we would simply average in our case of regression. And when we perform the single splits of the trees, the feature spaces will be partitioned recursively such that each partition has its own prediction. And the idea is that we try to find the best split within a feature such that we get the strongest difference between the two new partitions with respect to some kind of a splitting criterion. This is a bit depending on the implementation of the random forest and depending on the software. And so the idea is then that the observations within the same partition should be rather similar, while the observations from different partitions should be very different. So we try to make splits in this kind of sense. And there's also the idea that the single trees are pruned in order to lower the variance but increase the bias a bit. And this can be visualized in the dendrogram, which I want to show you for an example here for the FIFA World Cups. I chose this example because instead of the European Cups here, there is some famous matches that mostly all of you can remember, I guess, and then it helps a bit to understand this. So here you see one exemplary tree, and the first split was done on the FIFA rank difference variable at a certain split point. And actually we see on the left side are those observations where one team was the clear favorite team. And we can see that if we look at the box plot of the final response values within that final node, we can see, for example, there was the 8-0 of Germany against Saudi Arabia in 2002. And I think also once the Spanish team won 7-0. And we see in general that here quite large numbers of goals are possible. While if we follow this part of the tree, there was another split in the bookmakers odds variable. And here, for example, we see those teams which were not a favorite with respect to the ranking and also not a favorite with respect to the winning probabilities of the bookmakers. And here we see, for example, the famous 7 goals that Germany scored against Brazil in the 2014 half final when Germany was the slight underdog against Brazil. And here in this final node, we see kind of medium well teams. That is why here we have kind of a medium balanced box plot in comparison to these two. And that is how a single tree can look like. And now the random forest repeatedly grows several of these trees with the main goal to decrease the variance of the final prediction. And so what we have to do is we have to decorrelate those trees. And there is 2 randomization steps. I guess most of you know about this. So first of all, the single trees are not applied to the original data set, but to bootstrap samples or random subsamples of the data. And finally, at each splitting node, we don't regard the full set of predictors, but only a random subset. And in this way, we can decorrelate the trees and we get a nice trade-off between bias and variance. And that is why it's such a powerful method. And in order to apply now the random forest for football, well, as I already said, we take the number of goals as the response variable. We actually fit a large number of trees, in our case, 5,000. And when we now want to predict a new game or a new observation, we simply can drop the covariates down each of the 5,000 trees, resulting in 5,000 predictions, which we then simply average. And then the average number of goals that we expect for a game, which we can simply denote lambda hat, we can take it still as the mean of a Poisson variable when it comes later in order to simulate a tournament. And actually there's even more, but there's 2 famous implementations available in R, the very original one in the Ranger package, and then there is so-called conditional inference trees, a random forest based on conditional inference trees, which is implemented in the C-forest package, in the C-forest function from the party package, which is actually having some benefits when you have categorical variables. And as we have categorical variables, we decided to use this implementation for our purposes. Well, and the question is now, of course, how can we now find a good statistical forecast model? We have these Poisson models, we have the random forests, we maybe even have neural networks and other stuff. So what we decided is to set up a prediction competition, which we do as follows. We take our training data of the 4 preceding Euros, and then we do a leave 1 tournament out strategy. So we always take 3 out of the 4 tournaments as the training data. We fit all our different methods to the training data, and then we predict the single tournament that we have left out. And this we do such that each tournament is once the left out one. And this allows us to assess the predictive performance of these models in advance. And we compared, in our case, as I said, the random forest together with the classical lasso regularized models, the Poisson regression models, but also this time we also investigated a so-called extreme gradient boosting approach, the XGBoost, which is super powerful in these predictive competitions. For example, on the Kaggle prediction competitions, in these machine learning competitions, it's very often the winning approach. So we wanted to try this out as well. And we actually achieved a quite similar performance than the random forest. But as our data set is actually rather small, and this is a very complicated tuning approach, very complicated to tune, we actually had a bit better gut feeling to use the random forest. And so we stick to the random forest, which in our case was reliable because it also did a great job 3 years ago at the last World Cup. Well, and when you now fit our random forest to the 4 preceding Euros as a whole, then we can also check out the variable importance to get at least some interpretation. And then we could see that, for example, the market value and these logabilities from Achim Zeiler, from Innsbruck, from the bookmakers ability models, also the Champions League variable and Christoph's variable, which we find here, they are all rather important when it comes to the predictive power of this approach. And now that we have trained the random forest to the 4 preceding European Cups, we can take now the fitted model, and now we can take the variables of all the teams of the current Euro, and we have the tournament table from the UEFA. So we can now use the fitted model and can use it to simulate each single game of the group stage. Then we can follow precisely the UEFA rules and can proceed with the knockout stage. And we just have to take care a bit now of extra time and penalty shootout. And then we can also simulate all the knockout matches. And finally, we can simulate the whole tournament. And this we just did 100,000 times. And now we can simply count in how many times of these simulations, for example, did Italy successfully reach the round of 16, reach the final, or even win the final. And we see that we got a slightly larger probability for Italy compared to the bookmakers. However, we also had France and England as our favorites. There was one rather big gap between our chances for Spain and the ones the bookmakers provided. And also in our model, the Belgium team was a little bit lower chances, had lower chances than by the bookmakers. But in principle, it's comparable. And you could say that it's definitely a bit of a surprise that Italy finally did became the champion, as they were a bit kind of they were on place 7, so to say. Well, and now that the Euro is over, we can try to make some ex post goodness of fit analysis, which I actually just did today morning in order to give you very fresh results. And we see, for example, here we can do an ex post evaluation using classical statistical goodness of fit measures such as the predictive multinomial likelihood, classification rate, rank probability score. And we see if we compare ourselves with the bookmakers by using the bookmakers odds on each single game, they win, but we come rather close. And the classification rate, for example, there were just 3 games that the bookmakers predicted more correctly than we did. And we had actually a huge problem with the home effect for this tournament, because at the beginning of the tournament, we expected that there will be almost no fans. So we decided to exclude the home effect for the prediction. But lately, it turned out that at least England had games where they had a strong home effect, where actually they filled the stadium almost completely. So yeah, this is definitely something where we have room of improvement. I also
1 minute left, 1 minute.
Yeah, thank you. Finally, I want to show you the results in this kick tip round among 23 colleagues. The Sea Forest ended on place 5, which is also not too bad. We also participated in a forecast competition of a professor from Denmark, where the final tournament ranking is compared. The random forest was on place 4, close to the other ones. And finally, we also did some betting, simply betting on the 3-way result, which leads to the highest expected return. And at least we could win 20 euro by placing 10 on each game, which is kind of okay. At least we didn't lose money. There is some extensions on these betting strategies, but we used the most simple one. Yeah. Besides the references, I just want to thank you. There is a working paper where you can find all our results in more detail. And finally, There is also a blog that we had where we updated our results during the Cup. And finally, here you see me with an animal from the Dortmund Zoo, which I was competing with as an animal oracle for any German game. Thanks for the attention.
Thank you, Andreas, also for celebrating, also for celebrating Italy's victory with a title in Italian, so great. Let's move to the third speaker, and then we will have time maybe for some questions. So let's move on the talk by Jakob Söhle. Are you there with your screen? Okay, perfect.
Yeah. Welcome.
The talk is entitled Improving State Estimation through Projection Post-Processing for Activity Recognition in Football. Thank you, Jakob.
Thank you very much. So I will talk about activity recognition in football, and I will focus on two aspects. One is the performance measure, and one is a post-processing method that is kind of adjusted to this. So this is joint work with Michał Czyszewski, he's also in the audience, and Gert Jongbloed. And we are part of a bigger project, Citius Altius Sanius, focusing on health in sports. And there are sub-projects regarding 6 different sports or areas of sports. And then there are sub-projects on sensors, data science, and feedback. And we are in the sub-project data science. So activity recognition in sports, we want to give a summary of the performed activities during a training or during a match. And this is to improve the training and also to improve match results. And the long-term goal is also to link the performed activities to occurring injuries and to use this also for injury prevention. So the two main approaches for activity recognition are video systems and integrated sensors. We already heard about video systems. There you can see the running distance, for example. We will focus on integrated sensors. At integrated sensors, you can also focus on more local behavior without the person moving much. And advantages of sensors are they are fairly cheap. So they are very small and cheap. For video systems, sometimes it can be that players cover each other. So in that sense, sensors are more reliable and they are portable and can be transferred to other training sites or even to matches if it is allowed. So here we see the football data that we have for our project. We collected data from 11 amateur football players where they performed football-related activities like running, sprinting, passing, shooting, jumping. And then we have 70 to 100 time series per player, about 900 time series in total. And the players are equipped with a kind of sensor trousers where they have 5 sensors integrated on both shanks, on both thighs, and on the pelvis. And then there is an accelerometer and a gyroscope in each sensor. So we measure acceleration in 3 directions and angular velocities around 3 angles. And so here we have kind of labeled data. We know which activity was performed in which time series, but there's some time before and after the activity. So the activity is not cut out, or we don't have the precise duration of the activity, but just some time before and after, which was of course also due to the measurements, how they were performed. So we want to measure the performance of such classification methods, and we know that the activities cannot be arbitrarily short. So the minimum duration of an activity is typically around 1 second. So everything else is more kind of an artifact of a classifier. And also in this application, it's a bit unclear when precisely an activity starts or ends. So yeah, different people labeling the data will also come to different conclusion when precisely something ends or begins. So there's some variability, and the performance measure should take into account that activities cannot be arbitrarily short, and that it's a bit unprecise when they start and when they end. And we want to incorporate this by penalizing unrealistic short activities and also allowing for slight time shifts in the beginning and endings of activities. So how do we do this? We introduce some locally time-shifted distance. So here we have just two states, 0 and 1. So this is just for standing and some other activities, just to cut out the actual activities and separate it from the from the time before and after. We can consider cut-lag functions with a finite number of discontinuities, and then we want to allow for small time shifts, and we want to allow them up to size sigma. So that's some kind of upper bound of time shifts that we want to be more lenient about or want to admit. And this distance will just kind of sum up all the length of intervals of misclassification. But if there's an interval of misclassification due to a small time shift, we will just downweight the misclassification during that interval a little bit by factor W. So that could be even 0, then we would totally set it to 0 and not count it at all, but we can also just assign a little bit of weight of this. So then we have two cat-lag functions. We look at the union of all discontinuities and take the increasing sequence corresponding to that. And then here we have the length of the interval. This is 1 if we misclassify, 0 otherwise, and then we have the weight, and the weight is usually 1 only if there's the interval comes from a very small time shift in the transition of the states, then we downweight it by W. And so this takes care of this first point of the prior knowledge, that we have this uncertainty when something occurs or when the exact transition ends, but it does not exclude arbitrary short activities. So that comes next, and there we introduce the locally time-shifted measure, a performance measure, and we introduce a duration penalty for very short activities. So we just penalize each activity that has duration shorter than gamma with a factor lambda. And then we extend from function on the interval 0 to capital T to function on whole of R, just by setting it to 0 outside of this interval. And we introduce this performance measure, the locally time-shifted measure. Then by this locally time-shifted distance, we normalize it by the factor T. So that is then kind of normalized to 1 because it's normalized by the length of the interval. Then we have the duration penalty and we take e to the minus. So if the functions are close, then the performance measure will be close to 1. Now we want to introduce some post-processing method that kind of takes care and also excludes this arbitrary short time intervals or unrealistic short time intervals. So the post-processing method we see here, so we have, we look at a subset of cat-lag function where the state's duration is at least gamma, and then we project onto this set by minimizing the L1 distance and also having a penalization for the number of jumps. So the penalty for 1 jumps will be gamma 1/2, so that that automatically excludes durations that are shorter than gamma, because then it's cheaper to pay the L1 norm than to jumping twice. And we see such an example here where a function is projected, and and generally this excludes very short activities and kind of this oscillating activities. But the question is, of course, now how can we find such a projection? Because in principle, we are looking at a subset of Cadillac function, so it's unclear, and there could be very many different projections. But the good news is the jumps of the projection can only occur where the original function jumps, so that limits it to the finite number of functions, and then we can also construct a corresponding graph, a directed acyclic graph, a DAG, with weighted arcs. And then finding this projection corresponds to finding a shortest path in the stack. And the way the stack is constructed, the vertices corresponds to the possible jump locations, which are just the jumps of the original function, and the arcs correspond to corresponding segments, and the weights corresponds to the to the cost of this segment. So that is the cost of misclassification, but also including the cost for a possible jump. And then there's an algorithm that finds such a shortest path in a DAG. And the running time of this algorithm is of the order of vertices plus the number of arcs. And in our case, the number of arcs is quadratic, so it will be quadratic in the number of vertices. We can further improve on the computational cost by first kind of taking parts of the function only. So if we have long constant intervals, they separate the function into parts, and we can look at these parts separately. So the number of vertices is kind of the number of jumps of the function in one part only, not of the entire function. So let us now look how we can apply this to the football data. So here we just distinguish between standing and other activity, kind of the cropping out, isolating the activity from the standing part. We use the sliding window technique. So this is just a window with a little bit time before and after a time point, and then we just calculate the standard deviation. We have 5 sensors with 6 dimensions each, so we have some 30-dimensional data, and this translates then into 30 features, and we do some feature ranking by the relief algorithm and choose the 6 most relevant features. And then it's reduced so much that we can actually test all subsets of these 6 most relevant features and take the best subset for each classifier. We use also a cross-validation approach, also as seen in the Euro ranking. There was also cross-validation for the Euro cups. Here we use 10 time series for training and 5 time series for testing. So we kind of isolated the activities in 15, and then we used 10 for training and 5 for testing, and we of course rotated this around also. And here are the results. So we use different kind of classifiers: multi-layer perceptron, logistic regression, k-nearest neighbors, random forest, support vector machine, decision trees, and naive Bayes. And we see here the results. So in this locally time-shifted measure, the performance measure we introduced, results range from 0.59 to 0.916. And so they are kind of varying results, a little bit widely spread, and then we apply our post-processing method. And what we see is that all the results are now much closer together and in generally improve very good. So they improve and are much closer together. So in that way, the post-processing is adjusted to the performance measure, and we see that the actual choice of the classification method is now less relevant. Also, we have seen that the choice of the features is less relevant when we use the post-processing. So that makes the whole method more robust with regards to the classification method, but also with regards to the feature selection. Here, so the first paper is the paper that I talked about, and the second paper is just recent finished master thesis, where we applied a deep learning approach, and then we use this for the classification of the actual activities. Thank you very much for your attention.
Thank you, Jacob, for your very interesting talk. Let's move directly to the discussion. So please, Leonardo and Gigi, can you share your screen and start? Thank you.
Yes, Marika. So I'm sharing my screen. Okay, tell me if you can see my screen now.
Not yet. Yes.
Yes.
Okay. So first of all, thanks for the invitation, Marika. So thanks for this let's say, nice day invitation, because it's the best day in which we can discuss about football for us Italians, of course. So guys, thank you for your very nice contributes. So basically we have three contributes today, all of them about football. So the first one was about Christophe, who had a very nice overview about some current research and open question in sports analytics. So he underlines the role of players' relationship via network analysis and cluster analysis in basketball, but also by remarking, of course, the work from Paola and Marek, but also he underlines the very nice, let's say, aspects of positional data, which are even now more and more interesting at the time being. Regarding football, of course, he mentioned let's say the main, one of the main references in football analytics, which is the seminal work from Cardis and Tsouphras about the bivariate Poisson. But then he proposed a very, very nice approach on how generating a final rank league in case of a season stop. So basically, as statisticians and sports fans, we know very well what happened with COVID-19. So basically, he explained us how generating a new rank league, let's say the reminder of the season rank league, of course, when some matches are yet to come. So he showed us a very nice application to the League One 1920. I guess the methodology can be usefully applied to other leagues, of course. For instance, from Serie A or from the other leagues from the previous seasons, which was seriously affected by COVID-19. And then he ended with a very, very nice, let's say, question by remarking how many models are exist about football modeling, and let's say posing this very philosophical question, which is the best strategy for football modeling? This is a very open question. I guess that even after, let's say, the Euro Cup, there is not a unique answer, of course, and I strongly believe that the best strategy for football modeling heavily depends on the nature of the competition. Anyway, let's say that the philosophical question is very appealing, so I would like to discuss with Christophe and maybe also with Andreas, who had the second talk about this question. Andreas, in a joint work with Christophe and other colleagues, show us a very, let's say, appealing machine learning approach for the prediction of Euro 2020. I'm very impressed by the number of potential covariates who affect their model, because basically they had a very impressive work in collecting covariates, socioeconomic, ethnicity covariate, market value, bookmaker consensus, so many covariates in this very complex model. And basically in the literature, usually we know very well which are the so-called vanilla model with not many covariates. but it's quite rare to observe so many potential interesting covariates in the final model. So the random forests, of course, are very, very effective in terms of predictive accuracy. Of course, there is a sort of balance trembling between the statistical interpretation, of course, and the higher predictive accuracy. So, of course, Poisson-based models are more interpretable, but random forests are more, let's say, robust and let's say more reliable in terms of final predictive accuracy. Of course, the predictions obtained have a lower bias and reduced variance, and it was even, let's say, much, let's say, amused by the betting strategy because of course, choosing the outcome with the highest expected return is something that it's very well known among the bettors, among the bookmakers. And this is also something that personally I did during this Euro 2020. So thanks for reminding us which are the rules for an efficient betting strategies. And of course, England and Italy, which were the two Euro 2020 finalist teams, had of course the 30.5 probability and the 7.9 probability to win the Euro 2020. So let's say that their probability could seem not very high, but actually, of course, England was the second most likely team and it got the final. And it's not, let's say, a straightforward result because England never got the final, never achieved the final of a Euro Cup. And now a good question is, okay, what now for the World Cup 2022? In the end, the very nice, let's say, talk from Jakob, so which was different because he explained us labeling and let's say classifying player strategies for performance activities to inform athletes and coach via sensor data. So basically in the field which is called the human activity recognition. So of course, since the sensor generates raw data without annotations, which are going to suggest the use of unsupervised learning methods, of course, Jakob proposed a new performance measure, the so-called locally time-shifted measure, which addresses the issues of time uncertainty of state transition in the classification results. He showed us the results for 11 amateur football players with a sensor located on 5 different body parts. And of course, he proposed some very, very nice labeling techniques for human activity recognition. The post-processing procedure, which has been then proposed for binary activity recognition, of course, showed a better accuracy of classification methods. And of course, he used the tenfold cross-validation for all the classifiers by showing the, let's say, the supremacy of this methodology. So basically, I guess that Jakob can maybe usefully enjoy more data in the future, maybe more than 11 football players, and maybe do something as he stated about injury prevention. So in the end, we had 3 great talks given by prominent sports analytics experts with many technological factors considered. So sensor data, positional data, for instance, and with the development of our package. So for instance, Christophe mentioned the basketball analyzer package from Paula and Marika. And of course, also very nice prediction issues. So very open and wide questions, such as what is a good predictive model, especially now that the Euro Cup is over. And of course, even from the talks, it emerged, let's say, also the issue that how hard is predicting an international football competition. This emerged clearly from the talk from Andreas Kroh. And then, as statisticians, we know that there is always a conflict, let's say a comparison, between the predictive accuracy and the model interpretations. So I really appreciated, for instance, that all the 3 speakers dedicated a very, very good space to the, let's say, to the explanation of the methods, because of course, statistical methods need to be transparent, of course, especially then in this context where sports, of course, needs some very, very illustrative and transparent methods. Of course, although we try to predict football is full of rare events. And this is what is, let's say, the essence of the sports. So I want to really congratulate with all the speakers for their very, very nice, let's say, talks. Of course, maybe we do not have any time for questions, but thanks, Marika, for inviting me. Come on, Italia. We are very, very glad. And thanks thanks to the three speakers for their enthusiastic results and for showing us some very, very nice aspects from football analytics. Sorry, but now I'm it's very hot here. I'm thirsty. So thanks all, guys. And
thank you. Thank you, Leonardo. Yes, time is over, but I would like to ask just a very brief comment from each of the speakers, if you want, of course, to close the session. So, Christophe, if you want to add something, just a brief comment.
On the whole session, or?
As you want, if you want to reply to Leonardo about his question.
Oh, yes. I think this is just a food for thought. It's something that I've been thinking actually during the tournament. I think that perhaps what was a bit problematic in our predictions, as Andreas showed our model, were the transfer market values of the players. Because I think that nowadays, well, what we did, as Andreas explained, we made we standardized with respect to the highest number, but I still think that nowadays they simply don't mean the same as they meant like 10 years ago, because you have young kids that are just overrated and overly expensive, while someone like Chiellini will have a very, very low transfer market value. So I think that probably is something that needs to be taken out of that model. So that goes a little bit in what Leonardo said, what could be done here and there. That would be my take as a conclusion for 2022.
Okay, thank you. Thank you, Christophe. Andreas?
Yeah, I will just quickly add on this. So, I mean, I think we got in the end a way to deal with the market value problem that was quite okay, but definitely there was problems with the home effect due to this Corona situation, and that England changed during the tournament completely the strategy of how many fans could visit, and also some other cities like Hungary. They had a full stadium, while in Germany, I was myself in the stadium in Germany against Portugal, where there were just 14,000 people and very long distances and very calm. So that was a problem here. But in general, I would say that these machine learning models like the random forest and probably also the extreme gradient boosting, I think these are kind of the future, because they are a bit harder to interpret, but they definitely are good in prediction. And I also think that we are on the right track when we incorporate these additional variables, like the one that we received from Christoph, or the plus-minus rating that we received from other statisticians. And I think it's very good to join the forces here and build this kind of group, and to help together to build these models. That is really advantageous.
Okay, thank you, Andreas. Of course, it depends on the objective of the analysis. Jacob, a comment?
Yeah, thank you very much, Leonardo, for the discussion. Sure, we want to collect more data, not just in terms of numbers of players, but also more. This was a very controlled experiment, so we also want to have more realistic data with different activities after another, and just from real matches and so on. And yeah, of course, then it was just one step in the classification method we want to extend also. And I briefly mentioned this master thesis where we use deep learning, and we will go further. And of course, long-term vision to include injury data. Yeah, thank you very much.
Okay, so thank you everybody for being here. Thank you to our three speakers, to the discussant. Sorry for being late, and see you next time. Of course, everybody can contact the authors of this session to get some details and some more information about their work. Thank you. Bye-bye.
Yeah, and if you want to check out all the details, you can also just visit my website. We have there the link to the paper, and also to our blog, for those people that are more interested in the Euro numbers, just because it's so it's the time of the Euro, so fresh.
Yeah. Thank you
Bye-bye.
very much to everybody. Bye-bye.
Thank you. Bye.